Boom. There you go. Okay, everybody look at number 9 on green. Here is the equation for intensity levels of earthquakes and magnitudes. So if an earthquake happened right now, there are machines out there, these people that are called meteorologists or whatever, they study like the earth and whatnot and weather. There are these special machines that automatically know the magnitude. Yeah. So everyone write down the formula for yourself. Oh, I think it's already written. Yeah, so it's a Richter scale. So there are times, guys, when there's an earthquake happen and we don't even feel it. They'll say, like I've heard people say, "Oh, there was an earthquake last night," and I'm like, "Well, I didn't feel anything," and it's because it was so small. But we know there was an earthquake because then it showed up on the Richter scale. Kind of interesting. So we're going to be looking at and comparing how intense one earthquake is compared to another, given the magnitudes. So it says in 1812, these are true earthquakes that have happened. In 1812, an earthquake of magnitude 7.9 shook New Madrid, Missouri. Compare the intensity of that earthquake to the intensity levels of the earthquakes below. So there was also in San Francisco an earthquake of magnitude 7.7. We want to compare intensity levels. So everybody, I'm going to highlight what we're solving for. If we don't know intensity levels, that must be what we're solving for is I1, I2, kind of. We're not going to actually find the intensity levels. We are just comparing how much more intense one is than the other. So let's plug in what we know. So we would do log of I1, we don't know, intensity 1 divided by intensity 2 equals our magnitude of our first earthquake was 7.9 minus the second earthquake, 7.7. So now we actually have this. Log of I1 divided by I2 equals 0.2. Now you'd say, I'm trying to get these intensity levels. We're trying to look at intensity levels. It's trapped inside log. I need to undo log. Well, this is secretly log to the base 10. How do we undo log to the base 10? Base 10, both sides of the equation. Base 10 and log to the base 10 cancel out. I'm going to come up here. So the intensity of the first earthquake divided by the intensity of the second earthquake will be equal to, type into your calculator, 10 raised to the 0.2. Yes. Sure. Get the right answer. Okay, what decimal do I get? 1.58. So guys, that's about one. I'm gonna go with 1.6. So you guys, that's almost 2, isn't it? Pretty much, it's almost 2. So everybody, look at what this is saying. Now, right now I have this. Intensity 1 divided by intensity 2 equals 1.6. I've got to get myself some room so you can see what's going on. Now think about it. If I take and I'm like, well, I don't want to deal with, I don't want to look at division. The ratio, it is what we're looking at, but I'm going to multiply both sides by I2. So now look at what my statement is. The intensity, look, I'm going to say it as I read it. The intensity of the first earthquake is equal to 1.6 times that of intensity 2. So how much more intense was the first earthquake? Almost twice as intense. Does everybody see? Sweet. So the answer is it's 1.6 times more intense. That's our answer. Almost twice as intense. Or to be exact, 1.6 times more intense. So guys, that's almost double. Isn't that kind of crazy? Because that was a 7.9 magnitude, 7.7, and it was twice as bad almost. Kind of crazy. So if you were to look at the damage done on the first earthquake and second earthquake, in the first, it was way worse. It was twice as bad. It's kind of interesting. Okay, so right here, let's compare this one. It's huge. It's a huge difference. So in fact, 3.2, I believe, would not even probably be felt in real life if it was a 3.2 magnitude. When you start feeling things, when damage starts taking place, is in the 7s. So let's compare these ones. So let's do it. Log of intensity 1 divided by intensity 2 is equal to magnitude 1 minus magnitude 2. That minus that is 4.7, everybody. So now we would base 10 both sides. So now you would say it. Intensity 1 divided by intensity 2 is equal to 50,118 point something. So type into the calculator. 10 raised to the 4.7. So look at what this says. The intensity of the first earthquake was 50,000 times the intensity of the second earthquake. Do you guys see how 50 times as intense? That's 50,000 times as intense. That is truly the difference in magnitude. Isn't that crazy? Crazy. Okay, cool. Let's move on. So let's look at something different here. So a new equation here. So it says for pH given, because a lot of times they're going to give you random equations, and all we have to do with equations is plug in what we know, solve for what we don't, just like we just did a second ago. So it says for pH given, the concentration of hydrogen ions, H+. So here is the formula we're going to use. Now, what do each thing stand for? This is pH level. That's acidity level, I think. If you're a chemistry student, you'll know better than them. Okay, that's concentration of hydrogen ions. So it says for the pH given. So aren't we given pH? It says find the concentration of hydrogen ions. So in this problem, I'm going to be finding H+. So let's plug in what we know. We know our pH of 7.2 is equal to negative log of H+. So we're just solving for H+. Does everybody see? Good. Well, no. Yeah, I what would we do to get first? Well, first of all, we need to get rid of the negative. So divide both sides by -1. So we have negative 7.2 equals log of H+. Then you say to yourself, I'm trying to get H+ along, because that's concentration of hydrogen ions. Base 10 both sides. I want you all to type into your calculator because something interesting happened. So we have H+ equals, you get 6, type it in, 10 raised to the negative 7.2. 6.3, but then do you see the E? That means times 10 to the negative 8. So if we were going to write this out, that would be taking the decimal, moving it back 8 places, but we'll just leave it in scientific notation. So you guys, it was just algebra, wasn't it? Yeah. Very low concentration, sweet. So you could do, I don't think we need to do another example. You get the picture. Okay, cool. Let's begin today's lesson so that we can give you some time to work and get help. So we're solving logarithmic and exponential equations. You're going to need some room to write, like separate paper. Here are the step-by-step instructions to solving log and exponential equations. Now, guys, there's always correlation with solving different types of equations. Think about it. When I say to you solve a radical, you isolate the radical, then second, you undo the radical, then third, you solve for x. Same steps here. So your first step is to isolate the exponential or the logarithm completely. Nothing added, nothing multiplied, nothing divided or subtracted to your exponential base or your log. I'm going to write real quick. When I say isolate the exponential, I mean isolate the base or isolate the log. Then second, undo the exponential or the log by applying inverses. So now, just like what undoes a square root? A square. What undoes base 3? Log base 3. Right? Everyone? What undoes log the base 10? Base 10, right? So we're just going to apply the correct inverses. What undoes ELN? So then once we've undone the exponential or log, third, all you have to do is solve for the variable. And then fourth, we do need to check for extraneous solution. Now, I'm going to remind you, an extraneous solution is a solution that you get that when you plug it back in is not truly a solution of the original problem. We will only have extraneous solutions possibly for logarithms. If we're solving exponential equations, we're not going to have extraneous solutions. So if you check your answer with an exponential and you get it wrong, it's because you've done it wrong. So let me remind you, if I was to graph a logarithm, I would have a vertical asymptote at 0, and it would look like this, wouldn't it? So we know, since this is our x chart, we have all these positive x's. Yes, that's good. But then do you see how we will not ever have a negative x value in a logarithm? Do you see it ever go into the negatives? No, because there's not negatives inside a logarithm unless it's been shifted. So, and these, yeah, so, and then also, do you see how it never crosses 0? So let's say I got x equals 3 as a solution, and I went and checked it, and I plugged it in, and let's say the original equation was this. X minus 5 equals 10, okay, for example. Do you see how when I plug in 3, log of 3 minus 5 is log of -2? That cannot happen. You cannot have log of a negative. This would be considered an extraneous solution. Does that make sense? Also, let's pretend I would have had this. Let's say we would have got x equals 3 and I had log of x minus 3 equals 10, for example. I'm making this up. If I plug in 3, I would get log of 0. You are never going to cross 0, so that can't happen. If you try to type that into your calculator, log of 0, it's an error, because that can't happen, so then it would be extraneous. So if you have a negative inside a logarithm, not good, throw it out. If you have a 0, not good. But you have to check, because sometimes it will be positive when you plug it back in. So let's say I would have had a negative, okay, let's just do some examples and you'll get the picture. Here we go, number 3. So this is an exponential equation. It's not a logarithm. This would not have an extraneous solution. So we'll be able to check our answers and know if we're right or wrong right away. So the first step is to isolate the base. Now this is actually -1 multiplied in front. So you've got to take care of that first. You got to isolate the base. So divide both sides by -1. So now we have base 11 raised to the 7n equals 1. Is everybody good? We're going to kind of go quick. So now from here, we need to undo the base. You can't divide by 11. That's not how bases work. How do we undo base 11? Log base 11. Log base 11. You got to do it to both sides of the equation. So then log base 11 and 11 cancel out. 7n drops down. And now over here we have log base 11, and then remember it eats. It's like entrapping 1. Yes, it's good. So then on this side, just a reminder, if I asked you to type that into your calculator, you would need the change of base formula, correct? So this is where your ACT would then not have this answer. They would say, okay, so we have 7n equals, remember the change of base formula says we can rewrite this as log of 1 divided by log of 11. And then I'm going to want, so you guys are all shouting out the answer, which is great, but I'm showing you what I would want, a couple of different things I would want. Okay, last step to get n alone. Divide by 7. This is what I call the pretty answer. This is an exact answer with the algebra laid out perfectly in the order you did it. I want that answer. And I also, just because your ACT would stop there, I also want the decimal, whole number, fraction, or whatever. So everybody type in your calculator, log of 1, divided by log of 11, divided by 7. You all have to do it because I'm going to show you how to check it. So everybody needs to get the decimal right now. It's 0. So let's check the answer. So everybody, you plug, to check our answer, we would plug it back into the original. So go -11. Raised to the 7 times 0. Hit enter. You better get -1 or you've done it wrong. You get -1. We know we've done it right before we've even handed in the test. Okay, that one was easy. Let's do another one. Okay, number 4. Isolate the base, undo the base, solve for b. What should I do first? Add 8. So we have base 5 raised to the 3b equals 20. Can I divide by 5? Heck no, don't be that person. Log base 5 both sides to undo base 5. Log base 5 and base 5 cancel out, dropping down 3b. 3b equals, now what we have right now is log the base 5 of 20. Don't we need to change your base formula? So one more time, we have 3b is equal to log of 20 divided by log of 5, and then we have one more step to get b alone. Okay, so this is the pretty answer. You're going to have a little box with your answer. b is equal to log of 20 divided by log of 5, then divided by 3. There's your pretty answer. Then you'll say b is equal to, give me a decimal. Okay, cool. Let's read our instructions. How many decimals? That's 4 decimal places. So our answer is 0.6. 6205. Now, when we check it, we cannot use this rounded answer. We have to instead use the entire decimal. Now, we should not have to type in the decimal. Everybody remember, if you hit, so watch real quick. Okay, I'm going to go to my calculator. So I'm going to type in log of 20 divided by log of 5, am I right? Then divided by 3. I hit enter. Okay, there's the decimal. So now I'm going to check it. So I'm going to go plug it into the original. So I'm going to go 5, then second caret, raised to the, oops, didn't do the second part. 5 raised to the, what in the Sam? Oh, what the heck am I thinking? 5 caret, parentheses, mine needs parentheses. Isn't there multiple things in the exponent? So 3, I'm going to hit second negative. That puts in the last decimal for me. I don't want to have to retype it. Second after. Now look, I'm going to close my parentheses because that's the only thing in the exponent. And then I hit minus 8. If I hit it and get 12, I'm good. If not, I've done something wrong. Boom. Yes, because look at the original problem. We got to plug it into the original. Well, now you know you can use it. Sweet. Okay, let's do number 6. Moving on. Not any harder than a smiley face as a base. What should we do first? Should I ln right now? Heck no. What should I do first? Add 2. So rewrite what we have. E raised to the k plus 3 equals 78. Then, well, you'd say, okay, I got to get k down. I can't get it down unless I get rid of the base. How do we get rid of base e? ln, way to remember over here. So ln and en do each other. So then we have k plus 3 equals ln of 78. Now the nice thing is ln is a button on our calculator. We do not need to change your base formula. But still do not go to the calculator yet. I want the pretty answer. So k is equal to ln of 78. What? Minus 3. You'd say, okay, there's the pretty answer, and then she also wants the decimal. So now type in ln of 78 minus 3. I'm not going to show you how to do it. Everyone should do it, though. We're going to check our answer and make sure you're good with using the second answer key. So for our final answer, we are able to round to 4 decimal places, but when checking it, we're not. This is our answers. So now go like this in your calculator. E, then do your little caret thing, and then put parentheses. Then do second answer, plus 3, get out of the exponent, minus 2. Hit enter. You better get 76. Everyone should practice checking it. I wasn't going too fast. Well, you're going to be ready for 1010 and 1050 next year because it's going to be, you're going to learn 2 lessons in a day. Yes, so stop complaining. I'll show you karma on your grade, buddy. Any questions on this? Yeah, on purpose. So you can go back and stew over that. I hope so. He needs to know my true color. Hi. Did we get it? Okay, what I want you to do is work on 3 through 11, 45 through 60 like a maniac. Like, let's get that done before lunch. Check your answer on number 5. This is the pretty answer, and then you'd give the decimal. Yeah, remember, we can have negatives when solving exponentials, right? Not necessarily we can have negatives when solving the log, as long as when we plug it in, it's not still negative. Should have got that. If you're not getting that, get help. Check your number 7. This is the pretty answer. ln of 10 over 3.9 plus 7. Some people, actually a few people have asked me about 7. I'm going to do it. We have 3.9. E to the m minus 7 equals 10. You'd say, I got to isolate the base, so I got to divide by 3.9, first things first. So then I have e to the m minus 7 equals 10 divided by 3.9. Then you say, I need to undo e. I undo e by ln. Now I ln both sides. M minus 7 equals ln of 10 over 3.9. And then we would add 7. M equals ln, yeah, that. So with number 1, there's 2 ways to do it. And honestly, what's hard is, first hour taught it one way, second hour taught it different, and I don't know which one's better. Here's why. It just depends, honestly. So I'm going to do both ways. You pick the way you like. So everybody, way number 1. So notice with this one, there's multiple k's, correct? And then notice they're different bases. So I want to remind you, looking back at something more simple, if I have the same base, we can then just say x must equal 5 here, correct? So if we have the same base, we can just solve using the exponents. So let's rewrite 27 and 81 as the same base. So 3 to the what power equals 27? I don't know. 3 to the first, 3 to the second, 3 to the third is 27, correct. So right here we have this, 3 to the third, that's 27, raised to the negative 2k minus 3. Isn't that the same thing, just writing it different? Is equal to, and then if you keep going, 3 to the fourth is 81, so then we can say, well, that is base 3 to the fourth, raised to the negative k, and now I say raise the power to a power you multiply, so we have 3 to the negative 6k, distribute, minus 9 equals 3 to the negative k. And now because we have the same base, we can just say, okay, negative 6k minus 9 equals negative k. Yeah. Perfect. So that's a quick fix. Thank you for catching that. So now from here, we would add 6k over, correct? Thank you. Add 6k. So then we have negative 9 equals, if you add 6k to negative 4k, it's 2k. Solve for k. So you divide by 2. Therefore, k is equal to negative 9 halves. That's one way of doing it. We got the same base, and then we were able to solve. Here's way number 2. So some of you might like this way better. First of all, here's why some of you might, yes. Do you want me to answer your question? Well, here, we're just using the rule that once you have the same base, you can just solve using the exponents. We're just solving, so that's the true answer, like, right? Because definitely 3 is the same, right? So that will make this a true statement. So that's just the tactic we use to solve. Just like right here, we didn't put anything back in with the 3. It's just x equals 5. Yeah. If you'd have 3 times negative 2k, that's negative 6k. So we just have these exponents right here and right here, correct? So that's why I have negative 6k minus 9. And then there's an equal sign. So now we can solve. Okay, this is the other way. So the other way is to say, well, we undo bases with logs, don't we? How do we undo log base 27? I mean, how do we undo base 27? Log base 27. Well, how do I undo 81? Log base 81. But the thing is, we can't do different things to each side. So if you choose to do log of 81, you got to do it to this side as well. If you choose to do log of 27, you got to do it to this side as well. So I'm randomly choosing. I'm going to just go with, I'm going to log base 27 of both sides. Some of you might like this way better. Log of 27. Do you see how those cancel out? So then we have negative 2k minus 3 equals, now over here we have this. Log the base 27 of 81 raised to the negative k. And remember, because k is an exponent and we want to solve it, can't we take and move that down here? Properties of logarithms. So then we have negative 2k minus 3 equals negative k log of 27, log the base 27 of 81. So So then we would have negative 2k minus 3 equals, let me scroll up. Then over here we would need the change of base formula. So we have negative k times by log of 81 divided by log of 27. Calculate that for me. So I don't want to deal with logs. So we would have negative 2k minus 3 equals negative k times by, we would hit math enter because we would rather have fractions. 4/3. So isn't that just this? Negative 2k minus 3 equals negative 4/3 k. So then you'd say, okay, I'm going to combine my k's. So I'm going to add 4/3 k to both sides. It's just a linear equation. So negative 2 plus 4/3. Math enter. Someone for me? Negative. See, you had it right. So negative 2/3 k equals 0. Nope, equals, oh crap. This is what I really had. So I combined those. That was 0. So then I have minus 3 equals 0. This was the wrong way to go. That's okay. Add 3. So I have negative 2k divided by 3 equals 3. Then I'd multiply that by 3, wouldn't I? So then I have negative 2k equals 9. Then what would I do? Divide by negative 2. So k is equal to 9 divided by negative 2. That way it took longer. Okay, do this one however you want. Way the first way or the second way. Ready, set, go. Here we go. So way number 1, to get these as the same base. 6/25. You'd say, okay, well this is 25 to the first, isn't it? Let's see if we can write this as base 25 maybe. So 25 to the first is 25. 25 squared is 625, everybody. So then we have 25 squared raised to the 3x. You see how they're equivalent? Equals 25 to the first. So we really have 25 to the 6x equals 25 to the first. So what's my true statement? 6x equals 1. Therefore, x equals 1/6. Just as easy as to do it way number 2 in this one, where there's only one variable. We could log base 625 both sides. So then those cancel out. 3x equals log the base 625 of 25, right? So then we have 3x equals log of, change your base formula, log of 25 divided by log of 625. And then when we then just divide by 3. Then you would type it into your calculator, you'd hit math enter, and you would get 1/6. Make sense? Okay, let's review how to put logarithms together, because this is going to be important when solving in a minute. So everybody, remember, if you have two logs that are the same base, you can rewrite them as one log. So when you multiply, you add. When you divide, then you subtract, have a power to a power, and you multiply. And then it's backwards for logarithms. So there's two ln's, so we can write it as one ln. When you subtract, then you divide. So you'd say ln of parentheses, and now 16 will be divided by 8. So we have ln of 2. Now if it asks us to evaluate it, we could then type that into our calculator. It says, rewrite this as a single logarithm, so we're done. We've done that. That's just a review from last time. So let's do the 25. Now look, these ln's we could put together because there was nothing in front of them. Now this 3 is restricting us, and this b is restricting us from putting the ln's together. So let's fix them. Those are actually exponents, aren't they? So we have ln of a to the third minus ln of 2 to the b power. You'd say, oh, look, 2 ln's. That means I can write 1 ln with some parentheses. When you subtract and you divide, right? So a cubed divided by 2 to the b. And we've just written it as a single logarithm. Everybody good? Finish that section. 18 to 26. Okay, now we know if I was to give you x plus 2 cubed, it would be breaking the most forbidden of all forbidden rules to just cube that. And I still saw someone do that on their retest the other day. And I was devastated because we should not be making that error at this point. Can't do it. You cannot do it because of the addition sign. So everybody, looking at this problem, I want you to notice they're all log to the base 4s. This is what students tend to want to do. Base 4, base 4, base 4, and it feels valid. But here's the problem. There's a plus sign. That's like breaking the forbidden rule. That's like doing a exponent across an addition sign. You can't do it. So you can't undo a logarithm unless there's only one logarithm. Well, the good news is they're all log to the base 4s. So on the left side, we can actually create one logarithm by using properties of logs. Let's put them together. Log to the base 4 of, when you add, you multiply. So let's write this as one logarithm. Do you see the first step? We've got to put it together. One logarithm allowed only. So then we have that. We could multiply it in, sure. And then over here we have equals log to the base 4 of 24. So we use properties of logarithms to make it one logarithm. Now you can have one logarithm on each side of the equation. That's fine. Nothing's added or subtracted to those, so we're good. So now undo the log. Base 4, both sides of the equation. So now look what happens on this side. Base 4 and log to the base 4 cancel out. So then we have x minus 10 times 9 is equal to, and over here it happens to cancel out as well, equals 24. And then look, it's a linear equation. So now just solve for x. So I'm going to do it, you could multiply 9 in, or can we just divide by 9? So we have x minus 10 equals 24 over 9. Then we'd add 10. You would hit math, enter, enter. And you got 31. 30 what? 38 over 3 is the correct answer. It's not negative, so we're good, probably good. Like looking back here, if we plug it in, all is good. Did we all get it? Yes. You mean multiply 9 in? So then you would have 9x minus 90 equals 24. Then just solve for x. Add 90, divide by 9. It would work. Type it in. Let's all test it out for theory. It should work or something's going on. So unless I'm nuts. So do 24 plus 90, everybody. Divided by 9, math, enter, enter. You better get 38 thirds or else algebra is all of a sudden changed. Okay, cool. No, that's valid questions, everyone. Let's do another one. Look at 15. Now, once again, a lot of people, when they get to the test, go base 5, base 5, base 5. Can't do it because there's a subtraction sign. So instead, we need to put the logs together. But luckily, log base 5, log to the base 5. So we can write 1 log to the base 5. When you subtract, then so we have x squared minus 10 over 3. And that's equal to log to the base 5 of 2. So now we can base 5 both sides. And they cancel out on both sides again. So then from there, our true statement is x squared minus 10 over 3 equals 2. Now everybody, it's a quadratic. We solve quadratics by getting them set equal to 0 and solving by factoring. Or if there's no x, we can just solve for x squared, right? Isolate x squared. So look, there's no x's. So I can just solve for x. So I'm going to multiply by 3, won't I? So x squared minus 10 equals 6. Then when I add 10. Good, so x squared equals 16. Then what? Square root both sides. X is equal to? Nice! You guys are so awesome. You have to put a plus or minus for it. Now, it might be, we gotta make sure, is it okay to have a negative 4? It might be, as long as we plug it in and it's positive. So we got plus or minus 4, I'm checking it. If I plug in positive 4, that's 4 squared, which is 16 minus 10, is positive 6. That's good to go. Let's plug in negative 4. Well, if you use parentheses, negative 4 squared is 16. 16 minus 10 is 6. Still good. So both work. Because when we plugged it in, it's not negative. Both answers are correct. Moving on. 27. Solve for x. What do you suggest I do? Divide by 4. So now we have ln of x equals negative 1/2. Then e both sides. E and ln undo each other. So our answer is x is equal to e to the negative 1/2. There's the pretty answer. Then type it into your calculator. And round 2, it says decimals. It says to 2 decimal places. So you got 0.61. Are we good? Guess what your ACT would do? Your ACT would leave the answer like that, except they'd write this as the final answer. Are they equal? Yeah, because negative exponents get flipped. They might even go as far as to go like this. They might even go as far as to rationalize and have this as the answer. Because that would be the most appropriate answer. Because we technically don't have radicals anymore. But that's why we're going over it. Okay, cool. They wouldn't. They would not have something equivalent in value. I like something that's equal but less simplified. They wouldn't do that. Here we go. Number 28. What should I do? So we have ln of 3x minus 4 trapped inside is equal to 7/2. Now, we divide it by 2. E both sides. So 3x minus 4 equals e to the 7/2. Now what? Good. 3x equals e to the 7/2, and then we're adding 4. And then our pretty answer would be divide by 3, right? So we go off to the side and say x is equal to e to the 7/2. Then we have plus 4, and then we divided by 3. So now when you go to type this into your calculator, make sure you hit e to the 7/2 plus 4, hit enter, and then divide by 3. Otherwise, your calculator is not going to do it right. Or else use parentheses around the top. If I want that answer, and then also 28's decimal answer, you'd say also x is equal to 12.37. Now look, these ones you can literally check because ln is a button in your calculator. So this is what you should do. Go to ln, and then you'll do 3 times second answer minus 4. If you hit enter, we should get 7. You're typing it into the original, but checking with the entire decimal. Cool. 39. What should I do? Yep, combine them. ln, when you add u, so that would be 6x squared. Yeah? Sweet. Equals 3. Then, e it. I like that you know right what to do. 6x squared equals e to the 3rd. Divide by 6. So we have x squared equals e to the 3rd divided by 6. Now, next thing, square root, square root. So x is equal to plus or minus the square root of e to the 3rd over 6. So that's decimal, x is equal to plus or minus 1.83. Now here's what we got to do. Is it okay to have a negative in this one? Let's check. If we plug in negative 1.83, ln of 3 times negative 1.83, won't that be negative inside? That's bad. So in this problem, we say, okay, our only answer is positive 1.83, not negative, and then we will only have the positive exact answer because the negative got thrown out. Yes. 41. How about you guys do 41 all by your little selves? Go. And guess what? You got it right. Did you make sure to use parentheses around all that? I'll put this to rest right now. The correct answer is negative 0.93. You have to tell your calculator all of that's on top. It's the end of the lesson. So remember, when solving, if you have two logarithms, you got to put it together before you undo the logarithm. That is the end. The rest of the time is yours. You have about 15 minutes to get as many done as possible.